And good morning to all of my favourite humans. I acknowledge the traditional owners of this land. I pay my respects to their elders, past and present, and to Aboriginal elders and peoples from other communities who may be taking part in this live stream today. So, welcome! Okay, I do have a plan for today, but first, good morning everybody. Who have we got here? Dodgy's here, Austin, Chip, Johnny, Sion, doing the traditional moo. Moo. Oh, meow. Stephen, cool. Asked, has the schematic had any work since last stream? Yes, it has. And I'm going to show you some little sketching things that I've been doing in it. We'll get to that in just a moment. Andrew says, oh, John, I've got some Ubiquiti gear. USG Pro, Cloud Key 2, and 5-port flex switches. I'm happy to lend them to you to assist getting Superlab going. That would be awesome. I've just been the Cloud Key 2 I probably wouldn't use because I run the controller software in Docker on a NAS, on my Synology NAS, but I have actually specifically recently been looking for secondhand USG Pros because I am going to be moving one of the racks from the garage here and setting it up, and I want to go for rack mounted stuff. So I don't need a high-end router, and what I was thinking of doing maybe was just finding something like a second-hand USG, like one of the little security gateways, and putting it in a bracket, like a rack mount bracket, but something like a USG Pro would be fantastic. So, Andrew, that's a very generous offer. Thank you for that. And maybe you could be convinced to not just lend it, but to sell some of it. So anyway, let's talk about that. Who else is here? Gerald, Delane, Daniel. Yes, Daniel, he was right on time. I actually thought I was going to be late because it was about 2 minutes to start time, and I thought I really need to grab myself a drink because I always end up with a croaky throat by the end of it. So I went into the house to get a drink and came back out. The nice thing was that now that I've got all these macros and things set up on the ATEM with the Stream Deck, when it was time to go live, I just pressed the button and everything happened. It was magic. Sion says, is it shaving day? No, not yet. It's, what is it? I don't know. It's past the point where it's scratchy. It's actually kind of comfortable now, which is all right. Daniel, okay, yeah, so it's not good morning in Brazil, it's good night in Brazil, but thanks for coming along. Mike, yes, I want to look as cool as you. I won't get that. I won't get to that point, but yeah, almost grown up. Stephen W says, with a second Synology, you can be your own offsite backup if you set up a VPN between home and lab. Yeah, that's what I was thinking. So I've also been looking at secondhand Synology NASs because you can do a sync between them, which would be really cool. Problem is that I need a reasonable amount of capacity, because I've got all the video files and things, which means that although they could be excluded from the sync, but still, I've got my current NAS at home has I think it's 6 discs in it, 6 by 8 terabyte discs from memory, and buying 6 by 8 terabyte discs is expensive. So anyway, we will see. Right. Now, oh, Andy's here too. Yeah, water cannon plus shaver attachment should do the trick. Yeah, that's, if I go that way, the water cannon is still back there behind me. Yes, it does sound dangerous. That can be for washing off the shaving cream afterwards. So, where were we at? I'm not going to do a really big recap to start this off because otherwise my recap is going to be the first half hour and we're not going to get to actually doing anything. And I'd really like this time to be not just talking about the project but actually doing some stuff on the project. So I am going to instead begin by showing you some of the stuff that I did during the week. Last week we had kind of a pretty messed up schematic. Well, it's still kind of messed up, as you will see soon. And during the week I've been playing around with it a little bit more, experimenting with some ideas in relation to the power source selection stuff that we were talking about last week. And I'll show that. Rather than talking about showing it to you, why don't I just show it to you? So we can go to here. But first I need to bring it up. Where is the... Oh yeah, we will get to this. This is an important thing. It's probably the thing we'll actually start with, is fixing the footprint for this Ethernet connector based on some information that Austin has provided. So let's get everything up onto the external monitor so that you can see what's going on. Get rid of those libraries. Where am I? Project IoT AP. I always read it as IOTAP. It's my brain just can't not read it that way. What am I looking at? Schematic. Okay. Oh, it's also down here on the big monitor, but I'll bring it up onto the little monitor so that it can be on the live stream. Now, okay. Quick overview of where this schematic is at. It definitely needs a fair bit of cleaning up, and it needs some stuff deleted, and I need to fix the footprint for the Ethernet connector, as I just mentioned. And what I normally try to do excuse me is arrange the sheets of the schematic so that the logical blocks are grouped together in a sensible way. So for example, I will typically have all of the power supply related stuff grouped on a single sheet. And if there are multiple voltage regulators on a board, say we've got a high voltage coming in, when I say high, I mean it might be like 12 volts or 24 volts or something like that, and we need, say, a 5 volt and a 3.3 volt power rail, I will put both those regulators and whatever else is associated with them on one sheet so that you can look at one place and see how all of the power management is done without having to skip between pages. I haven't done that sort of proper rearrangement yet, so this is spread over a few different pages. But what we can see here on the first sheet is the Raspberry Pi Zero header, and there may be some changes here to switch over to using the second SPI port, SPI 1, not SPI 0. But we will get to that. There's a mode button, nothing too exciting, and the RGB LEDs. These are hanging around since the previous, what is that, B5? No, that's got to be fixed. So one thing we've got to fix is level shifting in the connection for the LEDs. Okay, next sheet. Next sheet we have Ethernet, and so we've got the Ethernet socket here with all its associated connections, activity LEDs and all of that sort of blah blah blah, coming across to the W5500 Ethernet chip and its associated odds and ends and things. Then we have a couple of other random things in this section. Oh, okay. Chip just asked a very good question, which is how will lumping the power regulators together affect thermal management? Why was that a tongue twister? Let me try that one again. How will lumping the power regulators together affect thermal management? I think I got it the second time. Okay, so there are two aspects to this. Three aspects. The first is that what I'm talking about here is grouping or associating on the schematic. So this is not necessarily the physical layout of how the board is going to go together. It is just the logical flow of electrons. So in the case of, okay. We'll get back to this sheet in a moment in more detail. I'll just use this to explain what I mean. This DP1435 here is a power over Ethernet regulator that spits out 12 volts. Well, that particular, it comes in a few different versions, but say we've got the version here that spits out 12 volts. And then we want to feed that into another regulator that's going to spit out 5 volts. And soon we are going to have a regulator, something else we've got to do today, which will spit out 3.3 volts. And you can see that the 12 volts that comes in from here is then going to go into the input of the 5 volt regulator. Then the output of the 5 volt regulator is going to go into the input of a 3.3 volt regulator, which is then going to go out to the 3.3 volt rail. But what I want to be able to do, for example, is when we're looking at the schematic like this, I want those regulators grouped together in a logical way. I may actually end up splitting this into 3 boxes. We will see when we get to that. But I want to be able to look at this and say, oh yeah, power comes in from these sources on the left and it goes into the input of this regulator and the output of that goes out to here. So that's not anything to do with the way those things are positioned on the PCB and how they thermally affect each other. It is to do with the logical layout. So that is thing one. Thing two is the layout on the PCB and the way they thermally affect each other. And if you have 2 voltage regulators jammed up right next to each other, then you get more of a hot spot on the board rather than having them separated. But having them separated, you also need to carry a power trace further across the board, which also may be detrimental. So typically the output of a power supply should be reasonably close to whatever is using the current from that power supply, so that you don't have, I mean, with the small boards we're talking about, this doesn't really matter that much. But if you have a power supply or a voltage regulator that is a long way remote from what it is powering, you have more of a voltage drop effect across the trace if there are sudden like fluctuations in current consumption, etc. So having at least the bulk capacitance of the output of the power supply close to the power consuming device is better. But, okay, let's not get into that too much. Back to this sheet. So we've got, on this one we've got the Ethernet, we've also got temperature sensor and Ethernet status. Ethernet status should be on this sheet because it matches everything else here. It's associated, but the temperature sensor is kind of a random thing. It may not belong on this sheet. But that can all be rearranged later. Now, back to this one. So this is the voltage regulator thing. And what we see here, if I zoom in, this part right here so that you can't really see so much, ignore this one down the bottom, just look at this one in the middle. This is almost how we left it last week. And what I've done since last week, at Austin's suggestion, was to replace the linear regulator that I had in here. I was running an LM7805, what's the variation, CT something, which is the automotive rated version of the classic old 7805 linear regulator. And they tend to run hot, particularly when you're pulling a bit of current out of them. And also Austin has been trying to track down some problems with potential power supply problems with things like the rack 32. And so his recommendation is to use an LM2596 as the voltage regulator instead. So the major difference from last week is that right here where this box is and the inductor, this used to be a 7805 voltage regulator, and all I've done is replaced the these parts right here. There is a Zener diode, the switch mode regulator, and the inductor. These parts here have replaced what was previously there, which was the linear voltage regulator. Okie dokie. So, what else? Oh, okay, yes. Now, I was messing around in here, sketching some ideas. Now, I've pretty much decided that what I'm going to do in the interests of just getting this working is in the short term, and ignore the problems down here. We're going to fix that today. That's part of the Ethernet socket question that we'll get to in just a moment. What I'm probably going to do is just leave jumpers in place here using the same scheme as I've been using in the past. So we're going to have manual jumpers that need to be put onto the board in order to bypass the power over Ethernet regulator and allow direct injection of, say, 12 volts down the wire. And last week I was talking about coming up with a scheme that allows auto selection of the power source. And you can see that I've made some notes to myself here about it. So then I just sketched out a couple of ideas. This idea here, once again, ignore the VB2 connections down the bottom. This was just experimenting with ideas. So what we've got is the output, how to explain this? Now this is kind of dodgy and I'm not sure that it would be a very smart thing to do, but what we can do is run okay, here's the logic. I'm going to do like a sequence thing. If we plug this into a power over Ethernet switch that supports 802.3 AF and it supplies power down the lines, and this PoE module negotiates a connection and it starts up its output, right here it's going to be outputting 12 volts. And that 12 volts is going to be fed into the input of the voltage regulator. But what we can do also is take that 12 volts, and it's from the inside of the diode, the anode side, take that 12 volts and use it to fire a relay. Now that relay over here has coils. It's normally closed, but when it powers up, it fires the relay, it opens these contacts, and it isolates this input, or these lines, from this source here, which would otherwise just feed directly into the regulator and bypass this. Now you can see that that is protected by diodes here, so that if this powers up, it's not going to backfeed into this, and we can't backfeed into any of these three inputs. Thanks for the reminder, Chip. Like for the algorithm, peeps. So now this is a kind of naive sort of scheme, because what it is allowing for, this would actually mostly work. Let me explain the problem though. If for example you put 12 volts or 24 volts down the wire using just a DIY injection scheme, what will happen is that the power will come through this relay, through these contacts, through here, and it will power up the regulator, and our device will get power. The power will also be on the input side of this PoE module, but this won't start because it doesn't have enough voltage. I've actually tested this with these DP1435s. I think they need something like 32 or 34 volts before they will kick into life. I have connected the input of one of these to like a lab power supply, and then just slowly cranked it up and watched when the output came to life. So this would not come to life, it would not do anything, this relay would not be triggered, and everything would work fine. So it works fine in the scenario where we are putting just, say, 12 or 24 volts down the wire. Now, next scenario, we connect it to a proper PoE switch, and it provides 48 volts. Like nominal 48, it could be as high as 56 volts down the wire. What happens then? Well, in that situation, this PoE regulator module does power up, because that's exactly the situation that it's designed to work in. So it does its negotiation, it gets its power, and then it outputs 12 volts on its output, and that 12 volts on the output fires this relay, which then opens these connections, and it disables the power coming directly to the voltage regulator. But here's the problem. That will take some time. It takes a moment, some period of time, it's not zero time, for the PoE regulator to power up and begin driving its output, and then it's going to take some finite period of time for the relay, because it's an electromechanical device, to energize its coil and then open the contacts and isolate these inputs. So until that happens, there could be up to 56 volts being supplied through this closed contact down through here and onto the input of this 5-volt regulator. Now, this is the problem. So there is a Zener diode here as a clamp. I think this is a 40-volt Zener, I can't remember. Anyway, there's a Zener clamp on the input, and where is it? I made notes to myself up here. So the Vmax on that voltage regulator is 45 volts. So because of the delay in the relay firing and this starting up, the input side here could conceivably be directly exposed to 56 volts for some period of time. Who knows how long? Could be, I don't know, 100 milliseconds or something, however long it takes for the regulator to start working and the relay to energize. Could be long, could be significantly longer than 100 milliseconds, I don't know. So the question is, can this Zener clamp deal with that for that period of time and absorb that amount of energy without going pop? And what will happen to this regulator in that meantime? So, yeah, so I just saw some questions. So this Zener here is for clamping. That's to stop excessive voltage being applied to the input. And this diode here is for the back EMF. So this is the one that goes across the relay coil. When the relay is powered up, there would be 12 volts applied on this side, and you can see that there would be no current flowing through the diode. It would just flow through the coil because the diode is reverse polarized. Then when this goes away and the relay, as the coil, as the magnetic field in the coil collapses, it temporarily creates a voltage in the opposite direction. So the bottom side becomes positive and the top side becomes negative relative to what's in the coil. And then that little spike of current gets passed through the diode and as the coil collapses. So that's the back, like the flyback protection or whatever it's called. And okay. So, problem is latency in the relay. So I started messing around. This is where it got to the point of I was thinking, screw this, I'm just going to leave jumpers in there for now. So the alternative is basically to replace the relay with a MOSFET, like a high side. So it'd have to be a P-channel MOSFET, and switch that off the output here. But even then, there's still going to be some period of time for which the regulator is going to be exposed. So anyway, what I'm going to do now is, and if we go to the board, you can see here that I've got a couple of different groups of parts. So there's like a big group of parts here and there's a big group of parts here. These are basically the duplicates of the power supply circuit. So what I'm going to do now, I was just sketching out ideas with this, and I deliberately left them in the schematic so that I could show you today, but I don't want to use them. So I am simply going to nuke those, and we'll be left with a single power supplied. I'm just going to leave those notes down there. So we're left with the simple scenario of the power supply, where we have the switch mode regulator here being fed from these. Now we need to fix this, which means fixing the excuse me, which means fixing the Ethernet connector footprint. And we also need to add a 3.3 volt regulator on the outside of it because what we need to do is, at the moment, what we have is 5 volts going into the Raspberry Pi. The Raspberry Pi itself runs at 3.3 volts. All of this I/O is at 3.3 volts. So it has its own onboard voltage regulator, and that is exposed here on this 3.3 volt output. The thing is, I've had a look at it. I'm not 100% on this, but I've done a little bit of investigation into the voltage regulator on the Raspberry Pi, and according to the specs, you're only meant to pull up to 50 milliamps out of it, because the onboard voltage regulator is also being used for the Pi itself and for whatever else it's doing, so you can't pull a lot of current out of it. In this circuit at the moment, the way this schematic is set up, this 3.3 volt coming out of the Raspberry Pi is our only 3.3 volt power supply. And that is being used everywhere, including down here for things like the Ethernet chip, which can pull significantly more than 50 milliamps. So what we need to do is isolate the 3.3 volt output coming from the Pi, and we need to add our own 3.3 volt regulator, which is capable of more current, so that it can run the Ethernet chip and whatever else we want on here that runs at 3.3 volts. So this 3.3 volt rail that we are seeing like all over the place, it's used for different things on the board, that needs to be supplied by our own regulator, not by the Raspberry Pi. Right. Oh, Stephen says your 25 volt input cap isn't going to like 50 volts either. Yes. Let's come back in here. Oh, you're right. That is. Funny thing is that what I don't actually use a 25 volt cap on that. That's what are they? This is kind of a sign of laziness. So this part that I put here, the Panasonic G footprint is it's just like a footprint that I use for caps that I put on lots of different things, and for power supplies and things. And the value here is 330 microfarad, 25 volts. It's probably not 330 microfarads, and it definitely isn't 25 volts. I should have fixed this in the value. In fact, it's just that Panasonic G footprint is one that I use really commonly. Let me see, what have I got over here, just as an example. I'm going to grab a... oops. That's, I just grabbed a real... What are these ones in particular? 50 volts. Yeah, but even that's not enough. Not for that side of things, because you need to derate caps. Electrolytics have to be derated typically 2 times. So we need like 100 volt capacitors. So these ones are an example of, these ones are actually high temperature and long lifetime. Like you can see, I've been taking cuts off that reel because my little DIY pick and place machine can't pick these up. I'm going to scissor that off, chuck it in the bin, get rid of the mess. So this is the sort of thing that I typically use in power supplies for bulk decoupling. You can see this one's 330 microfarads, 50 volts, and it is these ones are rated to, where is it? Yeah, 10,000 hours. You can see that the rating on electrolytic capacitors, typically they have like an operational rating within a certain temperature range, and these ones are rated up to 105 degrees for 10,000 hours, which is which is long. Like, these ones cost a bit extra because I wanted to get good quality ones. These go into like automotive projects, and it's more common to see like 2,000 or 3,000, sometimes 5,000 hours of rating at their temperature rating. These ones are rated at 10,000 hours. And these are the sorts of things that I use in projects like the water cannon controller. But but these ones are rated to, yeah, as I was saying, 330 microfarad, 50 volts. So as I think it was Stephen pointed out, that is a very valid thing. I need to change, let's change, what screen am I going to? This one. For now, let's just change this to 100 volts. But I'm going to have to make sure that, oh, hang on, no, what am I saying? 50 volts is enough in this case. Oh, no, yeah, it is enough if we don't use the auto switch thing. So that is a very good point. I'm going to make a, all right, I'm going to change this to 50 volt, but I'm going to put a note about that in, no, not there, in here for future reference. Yeah. Input side caps must capable of 56 volts plus, not including derating, if auto source selection is used. There. Okay. Yes. Oh, Austin said something about the LM2596. Yep, cool. I will look at that in just a moment. Thanks, Austin. Right. So anyway, where was I? Okay, so just to explain my thought process a little bit more. If we use manual selection of the source on this side, this rail here should never be exposed to more than whatever this outputs, which will be 12 volts, or what we send directly down here, which is probably 12 volts or maybe 24 volts. And if it's 24 volts, a 50 volt rated cap will be fine, because it's like a 2-to-1 derating. It's at least double the voltage that it's going to be exposed to, so that should be fine. But yes, you are absolutely right. This one says 25 volts. I'm just going to leave that as 25. For bill of materials purposes, C21 and C22 will almost certainly be the same part, coming off the same reel. So that'll probably end up being a 50 volt cap as well, just because we're not trying to optimize every single last cent out of this and use cheaper caps on the output side than on the input side. Easier just to use the same everywhere. All right, so it is almost time to get to Austin's input on the both the voltage regulator and on the Ethernet socket right here. So let's have a look at the voltage regulator first. Let's fix that up because that's kind of a simpler thing. Now, send a screenshot on the schematic you use. Okay, now Austin, you also sent me the board files for your ESP32 based Ethernet Duvalaki that has that connector on it, and I think it also has this same voltage regulator on it. Do you mind if I open those on the stream now? I don't want to do that without your permission, but if you are okay with it, I have those files and I can open them in Eagle right now and check that schematic and that pinout compared to what I've got here. So yeah, I don't know if you've put those designs up anywhere yet. So let me know. Hang on, I just realized I've still got yes, okay, cool, thanks Austin. I wasn't on live chat, I was on top chat. Thanks Austin, I can open them. That's excellent. All right, what I will do then is I have them right here, the WT32SC01 PoE board. This is something that Austin has been working on, and I don't have all the libraries for it, but this will be very, very useful when it comes to looking at, okay, so we've got the raw voltage coming in past a capacitor, same sort of arrangement as mine, coming into VN. We've got output going to the inductor, going to the output. We've got a clamping Zener on the, oh no, that's not a clamp. Yeah, that is. That is a clamping Zener on the output side. So that's not what I've got. Or do I have that? I don't know. I better check this. So what I'm going to do is I am going to screenshot this because I think Austin is right and I need to fix. Come on, screenshot, why aren't you working? Here we go. Now we've got a screenshot. So where are we? Just make sure that that screenshot got the thing. All right, and then I'm going to go back to the other one so I can do a quick comparison, because I may well have screwed up the, in fact, it looks like I did. I screwed up the schematic. I can see it already. What am I doing? Right, going back to here. Here, and here. Yes, I've screwed it up. I have definitely screwed it up. So, the issue now is going to be getting both of these things visible on the screen at the same time. Let's see how we can go with that. I'm going to move that over there. Can I shrink it? Shrink? Shrinkify? It would be really nice if I could live stream from the huge monitor instead of this little one, because it's really convenient having either a multi-monitor setup in this situation or a ridiculously large monitor and being able to view things side by side. So let's no, I should do it the other way. Let's do it this way. I'm going to move that over there. I'm going to move that so that you can see it up there, and then we're going to work. Also, I wish you could get rid of this view in the current eagle. In fact, let's let's drag it so that that's just off the screen. All right, now let's do a little pin analysis. Now there's already a fault here. This is in the wrong place. I'm just going to delete those nets and move that out of the way. Now, what have we got? Austin has pin 1 as VN. Oh, okay. First thing is I'm just going to check the pin numbers. 1 is VN, 2 is the output, 3 is ground, and I've got 2 pins on ground. Oh, ground tab, so that's pins 2 and 6. Yep, so Austin's got the ground pin on pin 3, and then there's the tab on the other side of it. So this is kind of a representation of the physical layout of the regulator. It's got pins 1, 2, 3, 4, 5 in a row on this side, and then the tab on the other side. So this is kind of what the regulator looks like. And what I've done here is not what it looks like, it's more of a logical layout. So we've got the input coming in. Hang on, I've got to mute for a second. So I've got input coming in, pin 1 on the left. All right, let's just check the pins. Pin 1, input. Pin 2, output. Pin 3 and 6 are ground. Pin 4 is feedback. Pin 5 is enable pin, or on-off, as it's labeled here. So my pin numbers match Austin's. And we've got input coming in on the left. We've got output. In Austin's, we've got output coming here, and it goes into one side of the inductor and also to that. So this is where I've screwed up the diode. Then we've got ground going to ground, which is fine. We've got feedback coming around here and picking up from the output side of the inductor. So we've got that here, feedback there. And then we've got the enable pin also pulled to ground. Enable, pull to ground. All right, so let's do a little bit of a move. I'm just going to drag all of this across a bit because this this here needs to be on the output, which is the input side of the inductor. Now do we match? Let's see. Oh, and also I don't like this, but I don't like having designators vertical. But sometimes you can't avoid it when they're ridiculously long. So I think we match now, Austin. Can anyone see any problems, any differences between this schematic on the right, which is Austin's, that we know works because Austin has used this regulator before and I haven't, and mine, which should now be the same circuit, but capacitance values, says Austin. Okay, so we've got 220 microfarad and I've got 330 microfarad. Yeah, I don't think that's going to make any difference. Oh, you've got 680 microfarads on the input side. Okay, so you've got a huge input side capacitor. That's interesting. I wonder if that's necessary, because that seems like a lot. What I could do is just put two of the 330s in parallel, because I don't want to have to get a different value capacitor. I'd rather just put down two of the same thing. So let's do that. We'll drag this across here, and I'm going to duplicate that and stick it in right there. This is going to need clean up because the yeah, there's nasty stuff overlapping on here. Oh, Austin says it's from the reference on the data sheet. Okay, cool. So maybe we do need we need like in the order of 600 and something microfarads of capacity on the input. Now we've got two of them. So we've got two 330s in parallel, which gives us 660 microfarad, plus or minus the 10% or 20% or whatever the crazy variation is on electrolytic capacitors. Okay. So hopefully now and 12 volts, yeah. 12 volts is a little bit misleading because it may not be 12 volts. The thing is that if we are running this voltage regulator with 12 volts output, oh, and the other thing I've been thinking about is, what about if I change this? So the DP1435 comes in multiple versions. And Stephen W. says, it seems odd that you would need a larger input cap than output cap when it's doing step down. Yeah, it does seem odd to me that the data sheet for that specifies 680 microfarads on the input side. That is a lot of capacitance on the input side of a buck converter. But anyway, I'm allowing for it now with the two caps in parallel. And I can just not place one or something if necessary. Easy to delete it out of the schematic. But we're covered now and we should be meeting the specs according to the datasheet. So this, see this says DP1435 SIL, SIL, single inline. Let's change the value on that. Yes, I want to change it because I want to make that the 5, no, not the 5 volt version. I want to make it the 12 volt version, because at the moment this comes in multiple versions. We can get versions that provide 12 volts out. We can get versions that provide 5 volts out. So one thing I've been thinking about is an alternative scheme where I use a 5 volt version of this PoE module, and instead of feeding it into the input of this regulator, I bring it all the way down and I feed it in at the output side, so that the 5 volt rail can be supplied either by this or by this. And that way, if we are using 802.3 AF, the other voltage regulator just becomes irrelevant. It's not even being used. So I am very, very seriously considering that as an option. Yes. And I've been going around that in my head, and I don't know which way is better. So I may still change that. What it would mean is, from a schematic point of view, it's actually incredibly simple. It would be, let me see, delete this, take this output, and stick it in there. Although there would also need to be a probably a diode here somewhere to prevent backfeeding into the output of this regulator. But still, you get the idea. So that one I am... Oh, Scott says, check out the output current specs of the DP module first. Oh, it's pretty high. It's a couple of amps. Yeah. Okay, Austin says, I have more trust in the LM2596 doing regulating versus the DP PoE module not failing. Yeah, the thing is though that if you are using PoE, like 802.3 PoE, this module has to be working anyway. If it fails, then we're screwed. It doesn't matter if this regulator is still working. And if you're not using 802.3, then you're not even using this regulator. So I don't think in terms of failure, it's actually one less point of failure in the situation where you're using, Stephen says 1.1 amps for the 12 volt one. Yeah, it's based on the power rating. And I think for the 5 volt one, you can get 2 amps out of it. So, I don't know. Part of this feels icky to me to be taking. So this module is a buck converter. It's it's basically the same as this almost. It's just a higher voltage rating. So you can feed 48 volts into it and it gives you 12 volts out. So what we're doing is we're using a buck converter and taking its output and feeding it into the input of another buck converter. Yes. Oh, okay. Austin says, yes, but if it fails, it will try taking out more other items with it, possibly going high volts, which I'd expect the LM to give more resilience towards versus the Raspberry. That is true. So if this failed and it started just exposing, say, 50 volts onto the input of this, the LM2596 would probably then just go into thermal shutdown and stop. And then the Raspberry Pi is not damaged. So it's limiting the spread of the converters. Yeah, Jordan, this is right. So Jordan says, seems much more efficient to use 1 than 2 buck converters. That's the other part of this. So if this is outputting the 5 volt rail directly, we're doing a single stage conversion with whatever its efficiency is. You know, I haven't looked at the datasheet on the 1435, but it's probably like in the 90-something% efficiency region, which, you know, switch mode regulators tend to be. So instead of having some losses here and then some losses here, you're only having losses in one place. Anyway, I am still quite undecided about that. But whichever path we go, then the output side of this still ends up being the 5 volts that we care about. So now, okay, I think we can close this now because I think I fixed the problem with the with that diode being on the input side instead of the output side. So thanks for that reference, Austin. That is really helpful. But let's now do something else. So what we need to do is we need to take, I'm going to change something. Wait, what was that? Oh, I was doing the wrong tool. So let's take this 5 volts. Let's make ourselves a little 3.3 volt regulator. We're not going to need a huge amount of capacitance on the outside of this. It's going to be a linear regulator. So let's stick in. What have we got? I'm just going to use the normal sort of thing that I use. Where is it? LB2985. I'm going to use which one? 1.5, 1.8, 2.5. I'm going to use that one. So let's stick in this. Yes, let's just make it 3.3. And what else do we need here? We need ourselves a ground connection. We need ourselves a 3.3 volt rail, and I need to change something on the Raspberry Pi. So let's just supply symbols, go, stick it there, that'll do. EN is active low. Let's move this over here. Input, output. Oop. No. Why I bent the wrong way? Because this is probably so small on your screen, I should zoom in. Alright, now ground, enable is active low, let's just enable it. Nothing connected there. We want, let's stick some kind of a capacitor on the output side. Let's just go for like a 10 microfarad thing for now. Cap, 0805. Just like a, which could be a bigger value, but let's just do this for now. What have we got? Oops, 10. I probably need some more bulk capacitance on the output side of this as well, but we can get to that in just a jiffy. So what we've got ourselves now is a little 3.3 volt linear regulator. It should be good for a few hundred milliamps output, and it is taking its input from the 5 volt rail, which is up here, and it's giving us a 3.3 volt rail. Now, the problem I just mentioned a moment ago is if we head over here to the Raspberry Pi, we can see that the 3.3 volt rail, so we're going to have dueling voltage regulators here. We're going to have the output from the, come on, show tool. We're going to have the output from the onboard regulator of the Pi connected to the output of the external regulator. So let's just nuke this and leave that. I'm going to stick a do not connect marker on that. And oh, there's my to-do list. So we've got the, okay, so 3.3 volt rail. We're now not using 3.3 volts off the Pi. That's better. And instead we're using it off this. So Now earlier, right at the start of this, when we started looking at this voltage regulator, like this power management thing, I said I might end up splitting this into 3 boxes. And this is kind of going to be dictated by the decision about whether this bypasses this. I don't know. Let's ignore that problem for now. Let's defer it. All right. What is everybody saying? AMS 1117 would be great. Oh, yeah. 50 milliamp seems low for 3.3 volts. Yes, this is not actually a 50 milliamp regulator. Like this footprint is the same one as I use with the 600 milliamp rated regulator. So AMS 1117 would be great. They're a lot bigger though. Yeah, 1117s are huge. Oh, Mike says, reminds that AMS 1117 has an unfortunate failure mode, almost always shorted. Ooh, that is unfortunate. Okay. Stephen W says, SOT 23.5. Yeah, that's what this is. So, maybe I am thinking of the wrong thing. Let's have a look at this, and this, and this. Yes. So this little thing right here, AP2112, this is the thing. It's the same footprint. In fact, let's value VR. Yes, AP2112K. That is the regulator that I would actually use. But let's go back to here and back to here. Yes. So value. Yes. I want it to be that, and I'll make it 3.3 volt. Okay. So this one fits on the same footprint, but it's rated to, I think, 600 milliamps. So that's the one that I have heaps of. I use these really commonly. Now, where are we at, people? Okay, time for some water. Austin, yes, next up, RJ45. Thank you for keeping me on track. While I'm doing this, let's add 3.3 volt reg. Done. Unify power supply designs. That was a note about about the different versions that I had. So replace linear reg with LMT596. We've just done that. Well, it was kind of already done. Auto switch PoE destination. I'm going to leave that as an open to do. And these are just mechanical related things that will matter more when we get to the 3D side of it. Oh, Scott says we're all lost because Steve isn't here to lead the chase. Steve is here. Where is Steve? Steve! Steve! Where is... Come on. Steve. I'm sure Steve was here. I brought Steve back from the factory. Where did Steve go? I'm not sure. I know I brought Steve home. Actually, Steve might be in the house. Not out here. No. Yes, I did bring Steve back from the factory because I was going to have him on the live stream today, and then I forgot to stick him over my shoulder in his usual position. Still in the car? No, I'm pretty sure I brought Steve inside. Now, that's right. So Austin was getting me back on track. The important thing, fixing this. Now, you can see this part number there is a ridiculous thing because it's like, okay, I won't get into the explanation of why. but it is dodgy. This has got to be replaced. What I started doing, all right, so now we're going to be messing around in library land, which can soak up a lot of time. And you can see I've already got it open here because I was messing around with this just before the live stream, trying to get things in a position where we could do something sensible. So I've been messing around with this footprint. And as I was doing this, I decided that it might be better to do things in a different way. So let's see. I'm going to, let's just create a new version. Just so, because I'm going to want to change things around, and it's going to block me from making more changes unless I do the create new version thing first. Creating server-side asset. Yes, syncing to the cloud. Damn it. I wish it didn't have to do this. Excuse me. Austin just said to do exactly what I was going to ask him for permission to do. I'm just waiting for this to finish its thing. All right, so before I get to that, I will just backtrack a little and explain. This part here, the Hanrun HY931147C, this is the one that I've used on many boards before. It's on the Ether 10, the Ether Mega, the Ether Bear, the Rack 32, and I've used it on, I can't remember, there are other things as well. I've been using this Ethernet connector for 12 years, I think, and it's never done me wrong. It's been really good with PoE, and it's a very well proven part with multiple sources available, not just original Hanrun, but there are third-party suppliers for it. So what I was looking for was that exact same part, but inverted with the tab on the top, so tab up instead of tab down. And the closest one I found was the ARJM 11D7 114AB EW2. And that's not much of a mouthful of a part number. So it's an Abracon connector. It turns out that Austin has been using that exact same connector, which gives me confidence that that is the one that I want. So this is where my process went off the rails a little bit. What I started was I took the symbol for the Hanrun part, and I made a version with the Abracon part with that same symbol, but the pins don't quite match up. I'm not talking about the allocation of the pin numbers, because the parts are almost a mirror image of each other, because one is mounted tab up and one is tab down. But the way it handles the connections to the transformer taps for power over Ethernet is slightly different. So I then ended up trying to munge the Hanrun symbol to suit the Abracon pinout, and that is where things went off the rail a little bit. So what I was doing this morning was basically I took the symbol and I gutted it, pulled out all of the other stuff, and I started putting on just the pins that I wanted, and then I was going to go back to the device and remap all of the pins. But let's bypass all of that, and no, that's not what I want. What I want is, I'm going to open Austin's project here. All right, so this is Austin's project doing Ethernet with PoE, and you can see it's the same module. It's a DP1435 here. So this is Austin's board, which is really cool. It's got some nice features in this. Like, look at these slots. Let's put slots in here so that you can, well, at least this is what I assume it's for. You can plug in the Ethernet connector, and you can see typically Ethernet connectors are oriented so that the port is on the edge of the PCB, so that the cable comes in from the outside of the board. But that's no good if you've got a device that you want to put in an enclosure or mounted on a wall. You need the Ethernet cable to be able to come in in the middle of the board somewhere. And this is exactly why Austin is using this connector, because if you look at this view, the Ethernet cable is going to come in from the right and plug into this connector. If the tab is on the bottom, you will not be able to get the cable back out again unless you like shove a screwdriver or something under it, because you can't reach the tab. And so what Austin has done is used the tab up socket, the Abracon socket, so that you can plug the cable in. The connector would be approximately that highlighted area there. That's kind of where the RJ45 socket would be, or the back of the cable would be sticking out of the connector. And then you can use these slots to put a cable tie around it and fix it in place. At least I guess that's what the slots are for. Very cool. And tab up. So this socket, now there are a few things about this that I would modify, but as a starting point, let's take Austin's suggestion, and so you can see here. All right, now this is an interesting question. The question of where should the origin point be for a footprint. And you can see that the origin in this case is in the middle of pin 1. That is really common, but it is not the way that I tend to do it these days. So we'll get into that in a second. But first, just make sure I've got the right library open. All right, so this is the process. For those of you who haven't seen it before, if you use Eagle, one of the nice things about the way Eagle projects are saved is that all of the information about the footprints and the schematic symbols is directly within the project. It's not referencing an external library, which means you do not need libraries to open a project. You can open a project and it is fully self-contained. Everything is there. With the exception of 3D models, that's a different thing because they're done through managed libraries. But if you want, say, a schematic symbol and a footprint and their associations and all of their variations and that sort of thing, you can get it out of a project. So in this case, what we've got is the footprint in the board file here, and the schematic. Let's come back over here. So this is the schematic symbol for the Ethernet connector, and they are associated just because of the way these things work. So this is different to things like KiCad, where at least it used to be different. I'm not sure with the most recent, but it used to be that with KiCad, if you opened a project file, you would need the libraries to really be able to make sense of it. But with Eagle, you don't. So what we can do is, if we want to take this part that exists in this project, so Austin has created this part and I want to move it into my library, then cool. Austin says, I got the footprint from somewhere else. I hate origin and the pins, but I'm switching to KiCad and thus not updating my old files. Cool. So what you do is you open the library. So we've got the library here and we want to move this part into our library. So you can go to either, I think it's either the schematic or the board file. I don't think it matters which one. You go to the origin, you right click on it, and we are going to do, and you can copy multiple things. You can either copy the footprint, the 3D package, or the device. And if you're in the schematic view, it gives the option of copying just the symbol as well. So what we can do is say copy device to library. Yes, let's do that. And it looks like nothing has happened, but now if we go into, actually, what is this called? Let's, 'cause I'll need that to be able to find it. You can see here it's got some attributes and things. Okay, it's an ARJM. Oh, and it's added the -2 because I already had one in my library. All right, we can fix that. So now if we go to our managed library and we go to the table of contents, we will see that there is an ARJM, etc. This is the part that I have just copied out of Austin's project, and it now has the footprint associated with it, it has a 3D package, which I don't think we'll have come across. No, because it's not linked to the managed library, so that hasn't come across. And it has the schematic symbol, this one. So let me do a little bit of cleaning up before we get into this. Can I delete this? I don't think it's been, yes, I want to remove that. What I'm doing now is just cleaning up my own mess that I made earlier. So what else did I have? I had another footprint somewhere. Where was it? Abricon. Oh, it was RJ. ARGM? That one. Yeah, this one is the one that came from Austin, and this is the one that I had previously. So which one am I going to use? I think to be on the safe side, I'm going to take the one that came from Austin, and I'm going to delete mine. So if I delete that footprint, but that is used in this part, so I'm going to remove that device, and then I'm going to remove this footprint, and I have to do it in this specific order because footprint isn't used by the following parts. Okay, yeah. Yeah, it has to be done in a specific order because it won't let you delete things if they're being used. Anyway, if I now save that and create a new version, that will clear out the part that I just deleted, and then I'll be able to delete this footprint. So I'm just cleaning up my mess, and then we are going to use Austin's part as the starting point because it's a proven footprint and proven pinout and all of that sort of thing. I am going to mess with it a bit, but we should be working from a good starting point. Here we go. Now, can I delete this? Yeah, there are some slight differences. Well, you can see obviously the orientation is different between these two footprints. In my footprint, I've got the EMC tabs displayed, visualized there. There's a keep out area or something on this one. The rotation is different, but let's just delete this. Remove. Oh, I still can't remove it because it's used by the 3D thing. Okay, that was what was blocking me earlier. That one. So let's get rid of that. Remove. Yes. Now can I remove this one? Remove. Yes. Okay. That's a relief. All right, now what we should be left with is just Austin's version of this part. Now, where is the footprint? There it is. Okay, let's change a couple of things. What am I going to do to this footprint? Well, the very first thing I'm going to do is move the name and the value apart so they can be seen. Now, what is that down there? Is that an orientation? It must be like, yeah, that's weird. Must be an orientation thing. I don't like it. So it's gone. Oh, that was weird too. Did you see how they'd done the orientation thing? So Austin said that he got this symbol from someone else. I'm just going to try moving this. What they've done to make a dot is done 2 arcs instead of a circle. That's just strange. Anyway. See, if I delete one, you can see that there's an arc there. Right, that's doing it the hard way. MH1, MH2, so we've got MH, what does that stand for? Mounting hole, I guess. So tab 1 and tab 2. And then we've got L for LEDs, we don't have the proper numbers on there. On the data sheet for the Abricon part, these have numbers, not L1, L2, L3, L4, but those are the LEDs. So we've got pins 1, 2, 3, etc. Now, do we want it oriented this way or which way? I don't know. I am slightly inclined to actually rotate this 180 degrees, and I don't know why, but no, I think this orientation makes sense. Yeah, Stephen said metal housing, MH, metal housing, yes, that's what that is. These are metal tabs that stick down. So, yeah, I think I'll leave the orientation as it is. I'm going to move this a bit further apart and move them away. Where is the origin? That's right, so our origin at the moment, this is messed up. Our origin is on the center of pin 1. I want it to be the center of the part. And this is where we can do some trickery and fun with eagle grids, doing some weird things. Okay, firstly, let's put it onto a mil. Yeah, that'll do. 50 mil grid. Now, the other thing is, oops. It's already got all layers shown. All right, now, ages ago on a live stream, I tried showing some trickery that you can do with grids. This is just a really simple example. Now, imagine, and you don't have to imagine because we've got it here, we have got a part that is at position 0, 0. This is our point of origin. We want to move the point of origin to be on the center of this main body, because, well, one of the reasons that I've really got used to this and I've moved to using center of mass as the origin is that it makes it so much easier when you're setting up a pick and place machine, because you don't need an offset to find the center point, like the centroid of the part for picking it up. So if you're going to be picking this part up, you want to pick it up here. You don't want to pick it up over here. That's just silly. Trickery I showed was late last year. Yes, okay. So what we've got is this part. Let's just fix the x-axis first. We're going to fix the two axes in two different moves. The first one is this part here. So we want to move the center to be midway between this pin and this pin. Now, what is this pin at? It is at minus 450. So we need to move the whole thing across sideways by half of that distance. So 225. And I'm probably going to totally screw up my maths here and everybody's going to laugh at me. But let's say, okay, so what we want to do is we want to move everything by 225 mils. And that's not millimeters, that's mils, because US units are stupid, but let's just go with it. So what we do is we change the grid to the amount we want it to move. So make it 225. So now what I can do is go select all and move, and if I grab this group, if I move it by one grid position to the right, it'll, you can see I'm moving the cursor slowly, it'll jump, goes boom, and now the origin is dead centered on the part in the x-axis because we moved it by half of the distance. Hooray! So now what I want to do, I'm just going to change this grid back to 50 mil and move this down here out of the way. So what we want to do is we want to put the origin right here, let's say between these mounting pegs. That seems like a sensible place to put it. And that looks like it's pretty much the center point of the center of mass of the part. So now we need to move it. We need to move it up by the position of these. So let's see where that is. That is at minus 250 in the y-axis. So let's set our grid to 250. Same deal again. Oops, let's move it over here. And move. I'm going to jump it up by one grid unit and boom, we are now centered. We've got our centroid right in the middle of the part. Now it took me, it's just taken me a couple of minutes of messing around to do that, and that was mostly because I was talking while doing it. If all you needed to do was move that by those two different offsets to the center point, I mean, that whole thing should have taken 30 seconds. And we now have a properly centered part. Hooray! Okay. Now let us go back to, Is there anything else we should do on that while I'm there? Let's just have a look at what actually is this docu. Okay, so it's a document layer. I don't know that that's needed. What have we got here? Because this will be docu as well. So the document layer is showing an outer bounds of the thing. I think that's a pretty useless thing. We've got the physical dimensions here. So I am inclined to just go yoink, yoink, boop, and it's gone. I don't think we need it. All right, let's go back to here. Now, where is the symbol? Here is the symbol. And similarly, I want to fix this because this symbol was created with pin 1. Okay, a couple of problems with this symbol. The symbol was created with pin 1 as the point of origin, which means if you want to mirror the symbol or whatever in your schematic, it's going to spin around in strange ways. So, yeah, so Austin said document area isn't used on silkscreen, it's for user reference. I use it sometimes, but in this case, not really needed. Yeah, that's right. So the T-docu layer or the document layer never actually physically exists on the board in any form. It is purely there as a visual representation so that when you're laying out the board, you can see things like the physical extent of devices when there is no silkscreen related to that physical extent. But in this case, it was just a box that was like around everything, so it wasn't even like a keep out area or anything useful. I don't think there was any point having that there. So this style of this symbol is not what I want. I have some general principles about how I do symbols, and once again, it's one of those things where you'll see me not do it, and that's because I'm not consistent. I am a strange, inconsistent person, like everybody. So what I do now is on the names, I always go bottom center on the name and value, and I normally have 0.066 as the size, I think, is my convention. So in here we're talking about, this is the grid on the schematic is always imperial just because that's the way it is. 0.066, and what am I doing? Bottom center. Now this doesn't matter just yet, but we will get to it. So then what I do, okay, the next thing to do is let's do a change size, come on, no, not length, that's what I'm looking for, to short, and go doink, 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 doink. No, better still, let's go group, select it all, and then do change, come on, short, and then change group, boom. So I changed all of the pins to the shorter length. Now I'm just going to change some names of a couple of things. What will we change? Instead of anode green, I'm going to just make that GA, green A, and then I'm going to make that GK, oops, for cathode. And then I'm going to do this. This is not really part of my standard, but this is because I want to rearrange this symbol quite a bit. I also want to delete something here, but in fact, let's rename MH1 to GND because we need that to be ground, and I'm going to get rid of MH2 in a moment, but I'm not going to be able to do it just yet because, in fact, let's try it. I'm going to try deleting it and I'll see if Eagle will let me. I bet it complains. Delete. You can't because MH2 is connected to a pad. So we've got to fix that. I will get back to that. What else do we want? So we've got data. Yeah, I don't know why, but with RD, so this is receive data negative and receive data positive, and receive center tap. My brain just prefers this to be Rx minus and Rx plus, and Tx minus and Tx plus. I don't know if I'm going to change them though. Probably not. I need to rearrange a whole bunch of stuff, but before I rearrange it, I want to fix the pins and get rid of MH2. In order to get rid of MH2, I need to go into the device and change the pin association up here. So we have MH2 here is associated with a pin, and I want to disconnect that, and I could do something else in this step, but I'm going to come back to it because I want to show you something. Now if we go back to the footprint, I can now, no, not the footprint, what am I doing? The symbol. What I can do now in the symbol is delete MH2. So we just have the ground, and this ground connection is going to go to both of those metal pins, the metal housing pins. But we only need one symbol in the schematic. This is something that I always used to do, was have, if you had a connector with say 4 ground pins on it, which is not uncommon because there can be like mounting pins and things that need to be grounded, I would end up with 4 ground pins in my schematic, and it would be like ground at 1, ground at 2, ground at 3, etc. But it's actually much neater to just say, the schematic symbol should not be a physical representation of the device. It should be a logical representation. So what we want is to show that ground parts are connected to ground. So what we have is one ground pin. And then back in the device, in the pin association section, we have okay, it's because I haven't saved it. It hasn't updated that pad. Okay, no, what am I saying? The pad is correct. Yes, all right. I had a brain fart moment there for a moment. So what I want to do is that second part that is on the footprint, it's currently floating and it's not associated with the signal. I want to associate that with ground, the same as metal housing 1. So I've got them both selected, and I can say append, and now we've got 2 pins, or 2 pads, connected to the one symbol. And you can see it's got MH1 and MH2, both connected to ground, which means that our schematic can now be neat because we've only got one ground pin. We don't have multiple ground pins that all do the same thing, totally useless. And all of the pins that need to be connected to ground are connected to ground. Now the other thing I'm just going to do is, no, I don't want that. I want, why? Eagle, why are you selecting that? Oh, it's because I'm in the wrong thing. I'm in the wrong thing. I should be here. I didn't want to do that. I want to do change, what am I doing? Change width. I'm going to make it 0.012, So 0.012 as the boundary width is the thing that I normally use. Now, next thing to do is going to be some major rearranging. So let's just start by pulling everything off. I'm going to grab all of these things and just move them out of the way. Let's stick them over here and move this up here and this over here. And what I'm trying to do now is center around the origin once again. You can see that the origin is way over here, and we want that to be the center of our part. And then let's stick name value. They are off grid, which really bugs me. Let's just make that 0, make that 0, and move, say, I may want to change this order at some point, but let's just go with this for now. I'm going to go transmit data first. So I'm going to do transmit data plus, then center tap, and then minus. I wonder if I should pull center tap off. No, I'll leave it there for now. And then I'm going to do receive data plus, receive center tap, and receive data minus. All right, very good so far. So we've got a logical grouping of those pins and they are in a sensible order. Now ground I will stick down in the bottom right because I always do that. And yeah, so Stephen says pair up VC pins, TX and RX pins with their center taps. Yep. Yep. Sorry, I haven't been looking at the chat. Looks like there hasn't been a whole lot of chat. Everybody's gone to sleep. Maybe what I should do is, when I'm doing this sort of stuff, I should make it like an ASMR thing. So, all right, let's freak everybody out now. And now we are going to move these. We're going to select all of these pins and I'll move them up here just to give ourselves a little bit more room. I'll move the ground down to here, but I don't have enough room for all of these. I can't keep that up. Now, where are we going to put these things? All right, I prefer the thing. I don't want to make this symbol too high. There is a trade-off here. Now, there is a trade-off here. Logically, most of the time we will want the pins coming off one side of the symbol, but that ends up making the symbol really high. If I put all of these pins on one side of the box, we're going to end up with a very high box with nothing on the other side. Essentially, it could be twice as high as it could be. But the thing is that most of the time, in the case of a connector, the nets are all going to have to go to one place anyway, or into one area, which means that if you make the symbol smaller by dividing the pins onto the two sides of it, which makes it half as high, you then have to run nets out and around to other places, and you end up with it twice as high anyway. So this is an area where I kind of go backwards and forwards. I can't really quite decide the optimal way to do this. I am tempted in this case. So the thing is that if you follow the principle of signals flowing from left to right and voltage from top to bottom, what we've got here is the higher voltage, the TD plus is high, TD minus is low. So top to bottom rule is met. Left to right, data is coming from here and it is going out to whatever device is going to be connected to this. Of course, the received data is kind of it's a mirror image. Data going back travels right to left. But yes, VC won't run to the same locations as everything else. Yes, that is correct. So this is why I'm bringing up this whole mental debate that I'm going through right now, which is where should the VC symbols go? Should they go on the left? And it is kind of tempting to put them on the left. So yeah, Austin says LEDs on left. That's where I'm leaning, because the thing is that, all right, I'm going to do it and I'm going to kind of explain it as I'm doing it. Let's just, let's mirror all of these, because I'm going to stick them on the other side now and then move them over to be here somewhere. I don't want it to be at the top. Okay, logic here. If this was an IC, up in the top left corner here is where I would have its VCC pin. So power comes in from the top left, ground is on the bottom right. So I do not want to put these right at the top, because that is conceptually, when I look at a part, that's where I see power coming in. These are LEDs. I'm going to put them down somewhere. And I know it's obscuring the name and value areas at the moment. We can fix that later. I'm just going to stick them here for now. Let's move that name up there and this value down here to get it out of the way. Now these things, if you think about it, these are kind of inputs to the connector, because these are to illuminate the LEDs that are in the connector. So inputs being on the left, that actually mentally works fine for me. And these will either be on nets that will wrap around. These nets are going to have to come out here and down and across and all the way around to the chip. Or they can just be stubbed and named nets, which is probably what I'll end up doing. So they can go there. Now, these ones, let's move, I'm just going to move these and then talk about it. VC, because this may not be where they end up living. But I'm going to put them here and then we'll decide if it seems sensible. Alright, so the reason for having these VC connections on here is that these are outputs that are used for power. So typically these will be supplying power from power over Ethernet out to, hey, cable tie, cool, thanks for coming along. Oh, Jordan said, I'm working also on an access point based on the IPQ6010. I've never heard of the IPQ6010, but that sounds like, well, interesting. Thanks, Jordan. I should check that out. So, in fact, I know this is, we have been remarkably on topic so far. I've just inadvertently woken up my voice assistant. Let's see if it says nothing. Oh, it's gone back to sleep. IPQ, what was it? IPQ 6010. I have no idea what that part is. Networking Pro 400 platform. CPU, blah. Okay, let's just click the first one and see what it says. Wi-Fi 6 networking platform, 4-stream Wi-Fi 6 networking platform. Okay, interesting. So that sounds like a far more sophisticated plan. What you're working on is far more sophisticated than what I am doing. But that is interesting, Jordan. Thanks for pointing that one out to me. Okay, yes, squirrel. It was kind of an on-topic squirrel. We needed a squirrel. Where am I? The fact that I've now got to reorient my brain and figure out what I was doing, that just shows that it was a good squirrel. It got me thinking about something different. Now, where are we? Okay, so we have the connections here that are typically used for, these ones right here I mean, which are typically used for connections to something like a power over Ethernet regulator. And so they are kind of considered outputs. It's a power source, not a power drain. So power from these flows out from left towards the right. So I think they need to be on the right hand side. So where I'm getting at is that this layout here, I wish there was a simpler way of recentering to the left. This layout here seems quite acceptable to me so far. I don't know if it's breaking anyone else's brain, but I think this is okay. We've got name. That's going to be replaced with like J2 or something, whatever the name is. The value, that is going to be a long value. So it's going to overlap with these labels here, and that's kind of bad. In fact, what I'm going to do is, I really don't like doing this, but I'm going to move the value label across to the left so that it is centered in the white space here, so that when it gets longer, it'll come out to here and out to here somewhere and not overlap too much with these labels. That really irks me, seeing it off-centered like that, but that's just the way it is. Jordan asked a very good question, which is what are the center taps for and how are they different from the VC plus and minus? So the center taps come off the output side of the internal transformer. It's the transmit and receive transformers have high and low side connections, like at each end of the coil, and they've got a center tap. And typically that will be connected to some noise suppression circuitry. Like it'll go to, just working from memory here, it'll be in the project, so we'll probably see it in just a moment if we have time to get to it. They're typically connected to a capacitor and a resistor, so like a basic RC network as a filter, and that provides some filtering on the output side of the transformer. Yep. Stephen said opposite side of the magnetics. Exactly. The VC pins are on the inside. Austin just said, I just realized with this connector, two of those VC pins are just pins 4, 5 and 7, 8, which means the connector might make it easier to design an auto switching system. Yes. Yes. Right. I don't think we're going to get to that today. But you are right, yes. Two of these pins are just pins, are two of the pairs on the 8P8C cable, or the twisted pair cable. UTP, whatever. I'm always using the wrong terminology and getting told off for it. Okay, I'm going to stop at this point with the schematic because I think it's close enough that my brain is going to deal with it. So, attributes that we have: name at the top, value at the bottom, inputs on the left to the LEDs, outputs for data on the right, outputs for power on the right. We have the ground connection on the bottom right corner, which is the convention, it's where I always put it. The body is an even number, an even width and an even height. So the origin is dead centered, which is exactly where it should be. And what else have we got? I've got 0.066 as the size on both the name and the value, which are bottom centered as their origin. And I believe we are good. We are good. All right. So let's just go back into the device and check. Variant, we've got all the pins connected. The only change was metal housing 1 and 2 both go to ground. So since Austin has already verified this pin out and I haven't changed anything else, we should be good there. And that's it. So let's do the thing where we do the create new version and synchronize this to the managed library cloud. So yes, Tony asked a good question, which is, am I correct that this connector has internal steering diodes? It's more than an RJ45 in magnetics. And Austin replied, no diodes that I can see. PoE module does have diodes. That's right. So the hand run connector that I have been using, which is the tab down connector, does have the diodes in it. Basically it's got two internal bridge rectifiers. And so what that allows it to do is have pins on it that are just like positive and negative output pins, which is really convenient. I don't think the Abricon connector has it. I think it's a little bit ambiguous in the datasheet, but the fact that it brings out these 4 connections for power instead of the way the hand run connector works, which is the 2 pins for power, it means that it does not have the internal diodes. And yes, I know Austin has already answered this question. I'm just kind of thinking through the logic of it. But the DP1435 has 2 bridge rectifiers on its input pins. It's got 4 input pins and each pair of pins runs to the input of a bridge rectifier. Alrighty, now where was I? Here, okay. Let's stick a 3D model on this. So we've got ARJM, blah, and I grabbed a somewhat dodgy step file. In fact, I don't think it's even for the same connector. But what I found was a step file for a tab up connector, which is approximately the same length. I think it's around 21 millimeters or so, I can't remember. Dropbox. And what I do is I have a folder in Eagle Extras, 3D models, and then I've got folders here for the 3D models that I import. So in connectors, what am I doing? DBRF, why don't I have it? What is going on? My model should be in here. It's not, maybe I didn't actually put it in the right place, but on my laptop, in fact, do I have my other laptop here? I think I do. I am going to, because this will only take a moment, I can fix this. This is a symptom of me not being thorough. So this is the laptop that I was using to do all of this. Where did I put it? It's probably in my downloads folder or somewhere still. No, maybe it just hadn't synced. I don't know what is going on. So Dropbox, Eagle Extras, connectors. No, it is not here either. Where on earth did I put that thing? Maybe I... Downloads. Let's try... No, this is going to find too much stuff. Molex, oh, I think I found it. Where is it? Come on. Oh, no, that's, what? No, that's not it. That's in diodes. Downloads. Diodes. I'm just going to open this and, or apparently I'm not. Open with PMDTM. That's not it, is it? No, I think that's something else. I don't know where this model is. Yes. Where? Yeah, I don't think this is it. I think this is actually a diode. Let's just load this model and see what happens. Or maybe I put the connector in the wrong place. PMDTM. I don't even know what that part is. But this is like the most recently modified step file I've got in there. And I might have... No, it is a diode. Where else? Where else? All right. Let's do something slightly different. And come back to here and go to GrabCAD because I'm pretty sure that's where I got it from. Sign in as me. Sign in. And okay, here we go. Library. What? Oh, that's a nice looking render of an Arduino Uno. Very nice. What am I looking for? Let's just try RJ45 tab up. Let's see what we find. That's no. Yeah, I actually had a bit of trouble finding anything useful, and I think I ended up, yeah, that one is tab up, but it's too short. Let's go to 100 per page. What I can do also is just put the tab down. See, there's a hand run tab up connector. What I can do is just put the model of the tab up connector on it. I'm sorry, the tab down connector. And it's going to show at least the correct physical outline, like where it's going to fit within the physical enclosure. Oh, look, there's one of mine. There's another one of mine. There's another one of mine. Where is a tab up? There's a tab up. Is that the right length though? Let's find out. This one looks actually kinda not bad. What is the length of this? I think I'm gonna grab this and just oh, it's an IGS file. Yeah, that's pretty horrible, but I think it'll do. Might have to pull it into, oh look, I already had it in my downloads folder. Show in Finder. Let's see if, ah, yes. Basically, oh, this is funny. We are recreating my path from before. You can see that there is this JXD. Okay. Let's go into Dropbox, Eagle Extras, connected, 3D models, connectors. Let's make a folder and call it RJ45. Just because I call it RJ45, not AP8C, and I'm going to stick that one in there, and that one in there. What's that RJ45 STP? I don't know what that is. And now, so what I had done previously was download that exact same model. Come on, I want to go up. But what I had done was opened it in Fusion 360 and converted it to an F3D file. So, and because Eagle can import Fusion 360 files directly, doesn't need a step or whatever, I can just upload that and then we can fix the position on it. Because I'm sure the origin will not be correct. It'll be at some crazy angle. Hang on, I've got to mute again to cough. Back again. There we go. Look at that crazy angle. All right. Let's spin it around, take it up right there, and spin it around. Oh, no, not that way. Where is it? The blue axis. We want the blue axis. Take it 90 degrees on there, and then we can slide it across on red. I mean, I could be doing this using dimensions, but I'm just eyeballing it because that's good enough for these purposes. Good enough for government work. Eyeball it to about there. Is that about aligned? Looks like it. And bring it down and seat it on the PCB right about there. Is that too high still? No, it's about right. And from the bottom, the things go through the holes approximately. Close enough. Yeah. That'll do, don't care. That'll do. Alright, save it. And that'll be close enough. GrabCAD, yes. Good enough for Australia. Yep. Alright, now, after all of this messing around, we now have the we should now have the RJ45 connector, and I can replace it in the schematic. So we're not going to get as far as doing any routing on the PCB today. But we've done some groundwork at least. A lot of board design is this sort of just grinding type work where you're going through get the footprint right, get the symbol right, get the model in there, check things against the data sheet. It's not the fun bit, but you've got to do all of this. All right, so now we've got that part in our library. I can close that, and this is Austin's project where I got it from. Close the libraries, back to the access point. All right, now, what I'm going to do I want to save? No, I'm not going to save Austin's project, but I am going to load this. All right, what we have here, we now need to replace this Ethernet connection with the, oh, and this is getting back to the question from earlier about the center tap. With this particular symbol, you can see very clearly that there's TX plus, TX center tap, and TX minus. The center tap is coming from the output side of that transformer, and here it's going into, it's a simple RC network. So we've got a 10 ohm resistor going to 3.3 volts, and we've got a 22 nanofarad capacitor going to ground. So that is a like a filter applied to the output side of the transformer. But on the input side, this is where the PoE output comes, and you can see here on the input side we've got two bridge rectifiers, and those bridge rectifiers together come to the PoE plus and the PoE minus outputs coming out here. So the difference between this one, the hand run connector, and the Abricon connector that we're about to change to, is that this one does all of this rectification internally. The output of those two bridge rectifiers is then combined. So you can see, for example, the positive side of both the bridge rectifiers is right where my cursor is now, and that comes up here, and that is the positive output. So what we have is all the hard work is being done for us directly inside the connector, and then we've just got a plus and a minus coming out of here, which is super convenient. We don't have that on the Abricon connector. Instead, what we have is two pairs of outputs, and then we need to deal with that ourselves. So before I actually go changing anything else much, all right, I will talk through my thought process here. This position, this actual mechanical position of this connector is exactly where I need it to be. So the new connector that we put in place needs to replace this one. There are two ways I can go about this. I can do a part replacement, in which case the schematic symbol is replaced with the new symbol, and the footprint is replaced with the new footprint, and they remain at the same origins. That means that when the new part is put in place, it's going to pop up onto the board in this exact same location. That only works if you've got direct compatible pinouts, and you can map from pins on the old part to pins on the new part. So it's probably not going to work in this case. So, Trady Trev said, but upside down. Yes. So the alternative, which is what I'm going to do, is to add the new part in without deleting the old part, and then fix the origins in the symbol, in the PCB. So let's do add part, and I'm going to go to my connectors library, and now we have our fancy new Abricon connector, and I can drop that symbol right there. So now we have the old connector, which is there, and we have the new connector, which is here, with a much simpler symbol that doesn't have all of the internals exposed on it, but that's okay. Oh, and that's ugly. Look what's happened here. The value, I'm going to move that value because that is horrible. The value was overlapping because it's longer. All right, so What we will have now though is on the board, it'll have plonked the connector down right over here, which is not where we want it. And the other thing is that this connector, if I look at the info on this one, you can see that it's mirrored because it is mounted up from underneath the PCB. This one is not mirrored, and it is sitting currently on top of the PCB. So there are a few things here to fix. First thing to fix is, let's grab the mirror tool and go yoink, and that is now mirrored. And now what I can do is grab this, and because it's on a grid, I can actually just drop it right on the same point of origin. And because the point of origin, when I modified that footprint, I changed the point of origin to be the center of mass right between these two pins, which matches the old footprint. I can just drop it on there and it will be in the same place. And you can see all the pins are overlapping, which is good verification that the footprints are good. So I'm just going to drop it right there. We now have two connectors existing in the same region of space, which is not good. But now we can go back to the schematic. So the reason I did that is that I just wanted to verify that I was getting the new connector in the exact same place as the old connector, so that it's going to be visible through the cutout slot in the bottom of the case. But now what I can do is grab my trusty delete tool and go, oh hang on, before I do, I just want to see, so activity is going to green and link is going to yellow. Okay, activity, green. Got to remember that. Let's go. Oh, and also I'm just going to look at a few more things. I'm going to just validate a few things before I delete this and don't have it available for reference. So from the W5500, I've got TX out, TXO positive, TXO negative, RX in positive, RX negative. And so RX negative, for example, goes to RX negative here. Okay, I wanted to make sure of that because this is the classic thing of TX and RX. Is it from the point of view of you, or is it from the point of view of the other device you're talking to? So what I can see here is that TX positive from the WISNet chip goes to TX positive on the connector. That is good. Alrighty, so now I feel reasonably confident in going, grab my handy dandy delete tool, green is activity, that is the final sanity check. Okay, so move, green, let's just put this over here, and before I forget anything else, I'm going to say activity green, I'm going to take this net and stick it over here, anode, yep, that one and that one. This is kind of a bit of a weird way of doing it, but let's move things around a bit more and stick that down here. That'll do. And that. Okay, so the reason I'm just doing this instead of making new nets is I just wanted to, well, I'm kind of lazy. And I wanted to keep the net names without having to remember them. So that way we know that yeah, let's make this a bit neater. We can bring this up here and bring that to say there, and where's our split tool? And so anode is there, cathode, I think this, was this right? No, I've got this wrong. These should have been going to, yes, the other, so it should be going to the cathode because these are supplied with the positive. Okay, I'm just going to delete this. Let's do this. because what we actually want is doink doink. I want this feeding the anodes, and then the outputs from the WisNet chip are actually like low side drivers for the LEDs essentially. So to make this neat, where can I get that to fit? There and there. Yeah. At the moment I am just trying to make this work. That is ugly. I'm going to fix that later. But at least now we've got the connections in place. I wanted to make sure those nets were connected while it was still in my head what the connections were meant to be. So let's get rid of some stuff here and move this over here. And I'm just going to move these out of the way for now. Those nets exist elsewhere in the schematic. What have we got? Okay, let's get our, let's shove those down here out of the way. And I've got those there as reminders for myself. Let's get our center tap filter networks all sorted out. Get that one over there. Pull this across. Come on, get ground out of the way. No, I don't want ground totally out of the way. That'll do. That can go there. And what am I doing? What am I doing? Center tap. That'll do. Let's stick a center tap filter there. And then we've got. Why did I only have a center tap filter on transmit and not on receive? I don't know why I did that. Anyway, I am actually past like when I should be finishing this live stream. So I think I'm gonna stop. Like I'm at the point now of just like shoving stuff around and rearranging it. I don't even know what that was going to. I'm gonna have to I'm gonna have to reference what I was doing before. But what I can do is make the important signals link. So transmit positive goes to here, and transmit negative goes to here. So this stage of a project like this, a lot of it is going to be just sitting here shuffling stuff around until it's sensible, like that. You know, just constant little improvements to make the layout of this schematic actually make a bit more sense. So let's bring these back here, and what have we got? RX positive. Let's take RX positive up to here. RX negative, take it up to there. So, you know, with a bit of sit here and grind it type work, eventually this will start looking like a sensible schematic that has things in places that look like they kind of make sense, and it's a bit more logical. So, we need a ground connection on that, and I prefer to have all my ground symbols at the same level. So this is probably gonna, like, this is all gonna get rearranged around in here. This is gonna get moved up and down and around, but eventually what will probably happen is that this will end up like on a line with this ground symbol. Wherever this one ends up being, this one might end up being higher up. I don't know yet, but they will end up more on a level. And also the high side, like the positive, I like those to be on a level. So this should be up at the same height as this one, just because it represents the potential difference. But for now, it's going to go back down there. So we have the start of the conversion. And now what I need to do, in fact, what I'm going to do is stub out these. I'm going to go V I'm just going to stub these out and name the nets. And I am also going to, no, that's not what I want. I want it to be that, and I want it to be 0.05. And there, and there. And name them. I'm going to call that one VA plus. This one is going to be VA minus, VB plus, and VB minus. And once again, as a reminder to myself that I don't actually have anything on these yet, I'm going to add, going to go to, shouldn't be in supply symbols, but it is. I've got it in the wrong library. I'm going to add not connected symbols on those pins and a not connected symbol on that pin, because I've got to figure out what's going on with the receive center tap and how it connects to the filter network. So what else have we got here? PoE V negative. Let's just delete these now, because we've now got the new things that are going to go to the voltage regulator. So down here we have VA1, VA2, VB1, VB2. In fact, what I should do is VB, I can connect these now. Let's do it. I'm going to get rid of that. Come on, get rid of the not connected symbol. And VB1, VB2. Should I call it VB1 or should I call it VB plus and VB minus? I'm not sure. Yes. Scott says lunchtime was 10 hours ago. Yeah, it was approximately 10 hours ago. So I've got a couple of options here. I'm going to name them one way and then talk about it. So VB1, I'm going to name this one VB plus, and I'm say yes to connect, which is a good indication that that net exists elsewhere in the schematic. So VB minus, and I'm going to make this one, no, I'm not going to change that. I am going to, what I'm going to do is change only this segment, and I'm going to make it VA plus, which is then going to re-link it to the other net, and I'm going to do this segment only VA minus, which will also link it to the other net. So what we've got now is the inputs on this DP1435 voltage regulator are coming from VA plus and VA minus. Now you can see here that VA1 and VA2 are the labels on the regulator. It's not plus and minus. Now that is because these inputs go into bridge rectify, so it actually doesn't care. We could reverse the polarity on this and it wouldn't care less. So there are two ways that I could do this naming convention. I could follow through the VA1 and the VA2 naming convention onto the nets, which would mean that up here what we would have is VA1 and VA2 instead of VA plus and VA minus. Now this is VC plus 1 and VC minus 1. I could use that naming convention. So what I've done here is split the difference. The name on the net is not the same as the input on the regulator, and it is not the same as the output from the connector. And that is probably not a great idea, but I kind of like it in a strange way. I don't like this naming convention, the VC plus underscore 1, VC minus underscore 1. That is not nice at all. But the thing is that what we're doing here is we've got positive and negative coming out of here. VA. Okay, I'm going to make it match. Yeah, okay, in my head I've kind of come to this conclusion. I'm going to make the naming of these nets match the input of the voltage regulator. So this is going to become VA1, and this one is going to become VA2. And then this one is going to become VB1. And this one is going to become VB2. Now, what that means is if we go back to the regulator side, we have got the pins here going to the regulator. VA1 is on net VA1. You know, the nets match the pins on the regulator. And that is an indication, so this is my thought process, that is an indication on the net that this net doesn't specifically need to be positive. It is the one input here, and this one does not specifically need to be negative. It is the one input here. Oh, sorry, yeah, the two input here. So then back elsewhere in the schematic here where we have those same nets, VA1, VA2, VA1 is the connection, VA1 on the input regulator, on the voltage regulator, which is VC, happens to be VC plus here. Alrighty, I'm going to delete these not connected, come on, they're not connected symbols, and I think logically that is a good way of doing it, because when we are looking at the connector now, we can see pin 6, which is VC plus 1, is going to VA1. I think that is quite clear, so I like that. I'm going to use that as the naming convention for that net. Where are we? Where are we? I don't know. Alright, so what I'm going to do is go back to my screenshot of Austin's schematic. Where did it go? Come on, open up. Screenshot, open. Did I just minimize it? It's probably already open and that's why it's not. Oh no, there it is. It was just taking a really long time to open. Oh no, I screenshotted the wrong thing. That was my screenshot of the symbol from the voltage regulator. Let us instead have a look at Austin's filter circuit on here. So this is the connector. We have that same connector and we have this on here. So we've got, okay, cool. So Austin's filter network is basically the same as mine. We've got 49.9 ohm pull-ups on the transmit side, and we've got 49.9 pull-downs on the receive side through this capacitor. And the receive center tap comes off the middle of this RC network. Okay, that makes sense. Cool. And the center tap on the transmit comes off this RC network. Alrighty. That makes perfect sense now. So that net that I had floating is actually the RC center tap. So let's go back to here. And yes, I know I'm over time, but I want to stop at a logical place. So the RC center tap, this one right here that I've got not connected. Let's get rid of that. It is the center of this RC network. So now that makes more sense, and that connects there. Very good. The layout of all of this still needs improving, but it is kind of close. It should technically be correct now. Like, it should be logically correct, even though it's a bit of a mess. Like, it's got this little dogleg in here, which ideally shouldn't be there. Which I could fix by just moving all of these back, which then gives me room to bring that across and make that a vertical run. This is the sort of thing where I would probably just sit here and fiddle with this part of the schematic for a while, not making any logical changes, because these nets now should be correct, but just making clarity changes and making the nets more obvious about where they go so that you don't have things crossing each other at strange places, and trying to keep to that high voltage up, low voltage down rule, all those sorts of things. So other things I've done. Okay, before I wrap up, I'm not going to make any more changes on this now. I am going to wrap up the live stream, but before I do, I'm just going to show you a couple of things I've done that I did while I was not on the live stream, so during the week. What I did was I did the assignments of the pins for the Ethernet chip. So we have, for example, here we've got the reset pin for the Ethernet chip is going to IO17 ETH-RST. And that is IO17 on the Raspberry Pi. So over here, IO17, Ethernet reset. It's active low, so I've got a pull-up resistor on here. There's a 10K pull-up, and it is going to IO17. So I went through and assigned the SPI connections. There is the mode button connection and Ethernet interrupt. Now, this is one of the things to decide. Right now, on this schematic, I have the Ethernet controller connected to SPI 0, so the first SPI port. So you can see it's for Kipo or Miso, whichever you prefer. It's using IO9. What we could be doing over here is using SPI 1, which is the second SPI port, and using IO19 instead of IO9. And Tony has been suggesting, oh yes, Tony Smith. In the chat, I just looked down and saw, Tony Smith, did you receive the overlay for SPI1? I think I did. I think I recall in my email seeing an email from you, but I haven't actually opened it yet. It's like in my huge inbox. So, so this is the thing. In order to make the Raspberry Pi talk to that W5500 chip, we need an overlay, which is SPI, oh, not SPI, it's Raspberry Pi speak for, it's like a compatibility layer. It is a mapping. It's almost like a boards file from Arduino land where, where you say certain signals or services are available on certain pins and that sort of thing. So you can associate the hardware and the way you've got the hardware set up to the way the software driver expects to see everything. And then oh, cool. So Tony said, we'll post on Discord what is an overlay. Groovy. Hopefully my explanation wasn't too bad. So we can use an overlay that maps SPI for this particular driver onto these pins, or we can use an overlay that maps it onto these pins. And what Tony is suggesting is that I use SPI1 instead of SPI0. And this is the reasoning behind this is thinking ahead a little bit to other devices that we might want to put inside this access point. Imagine we wanted to add some other device that used SPI, and we are using SPI for the Ethernet connection. Now, on this, the Ethernet is basically going to be the bottleneck. Pumping data through to the WIZnet chip is going to be the performance bottleneck, and we don't really want anything else on that same SPI bus. If we have other SPI devices, ideally they should be on a different SPI bus so that there is less opportunity for contention between them. So, and the thing is that things like drivers for SPI devices might be assuming it is on the first SPI port. Now, Tony, hopefully I'm explaining your train of thought here clearly. Tell me if I'm not. So if in future we want to add another SPI device and its driver assumes it's on SPI 0, then it would probably still work with the WIZnet chip on there, but we would have two devices on the same SPI bus. And then we have the data, which potentially is very high rate data. We're pumping as much as we can through the Ethernet connection, through the WIZnet chip, on the same bus as some other device, which might be also using up some of our SPI bandwidth. So by moving it onto the second SPI port with an appropriate overlay, we just avoid that whole problem. And so at the moment, the way this schematic is set up, it is still on SPI 0, but Tony has been doing the work to make an overlay to make it work on SPI 1. So probably the next thing I will do is change the pin assignment. So, what the hell? Why don't I just do it now? It'll only take a moment, and that's probably as good a place as any to wrap up. Right. Oh, interesting. Austin says, yes, having that exact issue with an ESP32 and the W5500 library not having provision for specifying the bus, thus causing a conflict, slowly modifying the library to fix the issue. Yeah. So, yes, Austin has faced the same problem. But if Tony has got the overlay working for this, then the software side of it is taken care of, which is awesome. So thanks for looking into that, Tony. So what I'm going to do now is, where am I? I am going to go Shift Command 4 and take a screenshot of that. Kadoink. And it's going to appear on my desktop in just a moment. Here it is. So this is the screenshot that I just took showing those pins. I'm just going to move that down off onto my other monitor for now, because what I'm going to do now is go to the WISNet chip. Here we go. Now, over here, this is where it is connected to SPI 0. I'm going to remap these pins now. So I'm going to rename this net. Come on, rename. And okay, so this is the sequence. At the moment, this pin 34 is connected to Keepo on SPI 0 on the Raspberry Pi. We want to remap it so that it connects to SPI 1, but I do not want to rename the net that is on the Raspberry Pi. So I'm going to say this segment, not all segments, and I'm going to change it to map it to IO19, just Keepo 1, and if I hit enter, it'll ask if I want to connect. Yes, I do. So that has now changed that mapping without changing the name of the net, and we'll see that in just a second. And now I'm just going to repeat the process. So copy on SPI1. What I'm looking at here, just to remind myself, is on the other monitor I've got this screenshot showing the pinout with these names up here. So for I want IO20 copy 1. So I'll move it down out of the way. I want IO20. It's basically 10. It's just 10 pins up. Copy 1. Okay, yes, connect. And the clock pin I want to be, what is clock on the other bus? 21. Yeah, it's all just SPI 0 and SPI 1. They're just 10 pins apart, all offset by 10 pins. So yes, I want to connect that. Now IO8 can still be the Ethernet chip select, most likely. But Tony, if you have opinions about the... oh, Tony, yes, it's already working. That's fantastic. Thanks so much for looking into this and prototyping it. So if you have opinions about what the chip select pin should be, Tony, are you using IO8 as chip select, or are you using something else? That would be very, very useful to know. So now let's go back to here, and we now have the nets. Okay, can only work on CE0 at the moment. GPIO 18. Okay, cool. Well, in that case, how about I make it GPIO 18? Let's stick... Whoa, no, wrong thing. I want a net on there, and let's name it, and we'll call it IO18CE. We could call it CE0, chip enable 0, just to make it really clear. Although it could be, no, let's add ETH into it so that we know that it's for the Ethernet connector. And in fact, I'm just going to copy that net name and come back to here, and the chip select or chip enable or whatever it is, I'm going to rename that. Instead of being on IO8, I'm going to link it to that. And make that, yeah, I'll put the bar over that, and then I'll rename the other one to match. Come on, rename tool. Put the bar over the end to show it's active low. Yes, I want to link it. And now I can delete these not used things. Oh, hang on, let's take that one and move it and go copy clock. And so I am no longer using any of these things. And so what I can do is rename IO8. It's no longer Ethernet chip select, it is just IO8. And that's it. We should now have our Ethernet connected to the second SPI. Okay. Tony says, hope to get it working on fixing that problem in the existing overlay, trying to get it working on chip enable 2, GPIO 16, which is next to the other pins. All right, yeah, I haven't even been looking at the physical layout of this. Let's have a look. Okay, so we've got these are the SPI connections here coming down to the WISNet chip. So they're coming from that right-hand end. It might actually be worth spinning the Raspberry Pi around entirely. That could be a sensible thing to do. Let's just get rid of some of these and do this. Angle, I've got to unlock it. We're locked. Got to unlock it there and apply, and then I can make it say 270 degrees and apply. And rat's nest. And now we have shorter traces coming to this area here. That seems like a sensible thing to do. Right. Oh, we got some power supply things just hanging out here on their own, having a little party all by themselves. Let's just move these things over here. And yes, I really am going to finish this live stream. The thing is that once I get onto this sort of thing and my brain is engaged in this process, I just keep going. Yeah. So let's just, let's lock this back in place. Now, Tony, you were talking about using IO18 instead. Oh, Tony, gotta go. Well, thank you for coming along, and I will check email for sure. But for now, it works on IO18. It's not like this is a tight board. There is heaps of room on this for running traces. I don't have a problem with using IO18 as the chip select pin. So there we go. I think we're in a more sensible place now than we were at the start of the live stream, which is always a good thing. Now, to do, before I do finally wrap this up, I am just going to fix the to-do list, because this is now broken. This alternative PoE input is broken. I could fix that now. I am going to resist the urge because I need to eat, and this live stream has been long already. So what I'm going to do is add a to-do in here, which is going to be the highest priority item, and it is going to be link PoE, what am I going to say? Link PoE from connector to bypass jumpers. Okay, that'll make sense to me, I think. So my problem here, what we're missing is if we go to this one, okay, if we go here, we have these connections coming out of the Ethernet connector, VA and VB pairs, and they currently go to the input of this PoE regulator and absolutely nowhere else. And these jumpers are now orphaned. They are going, in fact, no, I won't. These are now going absolutely nowhere. So this PoE V Plus that comes into this jumper doesn't connect to a thing. There's nothing at the other end of that, which is useless. So what I'm going to do is figure out the appropriate connections. But I'm not going to do that now because I am hungry. You can do them upside down with bond wires, flip chip. I'm going to instead, I'm going to quit out of that. Save, yes, I most definitely do want to save. And pause for a breath and have a look at the chat, because I just saw people have been talking about flip chip and bond wires and stuff. What did I miss? Chip said, it is a pity you can't turn components inside out. Or buy an XXX-R model. Yeah, rotated or reversed. Oh, Austin said, also I recommend RGBW LEDs. Okay. So, just in place of the regular WS2812Bs or whatever they are. Double throw, dual toggle, and a relay. Yes. Yes, I talked about the issue of a toggle switch last week, and a toggle is tempting, but as I said last week, it is too easy to screw it up without thinking about it, because you can flip the switch into the wrong position, plug it into a PoE Ethernet switch, and apply high voltage where you really don't want high voltage. If it's jumpers, you have to actively think about it and consciously put the jumpers on, so there's less likelihood you're going to screw it up. Right. I really need to pause for breath, which means I need to stop and get some lunch. And because I've been talking for now 2 hours and 40 minutes straight, my jaw is starting to hurt again. I don't think I mentioned this. Yeah, I didn't. Last week on the live stream, I mentioned that my jaw was starting to hurt after doing the live stream for so long because I'd had the wisdom teeth out. And during the week, I went back to the dentist, and it turns out that I have dry socket in the left side, which means the bone is directly exposed. The blood clot didn't form properly. And so that explains why it's been hurting a bit. And now the right-hand side has healed pretty well. The left-hand side, there's still a bit of an ache in there because I've got that dry socket. But it is healing, it is getting there. But it means that at the end of 2 hours and 40 minutes of continuous talking, my jaw is actually aching because it is still in that healing stage. Okay, thank you all for coming along. I hope you have a fantastic week, and I will talk to you all really soon. And also, it is quite likely that I'm going to have a guest on next week, an actual live guest on the stream with me. Uru Chip, see everybody else, and I will talk to you soon. Thanks, bye.